All right, for chapter 12, section 3, part 3, we're going to talk about one of the cool applications of matrices, and that's helping us get information about directed networks. We have some special guests for this video. We have Pizza Pie Chef. I love the matrices. Some kind of, I think he's like a train engineer or something. And Mr. Patnod. All right, you guys ready to learn about matrices? I'm always ready to learn. All right, let's go. First of all, let's talk about what is a directed network. And, well, maybe we want to talk about why would we want to learn about directed networks. Yeah, why would we want to learn about directed networks? Well, directed networks play an important role in different types of applications, like traveling between cities and setting up airline routes, and also food webs, which maybe Mr. Patnod knows something about, because I think he teaches biology. Correct? All right. Let's talk about, oh, and the pizza pie guy knows about food. I love a food. All right. First of all, what is a network? So a network is really just a set of connected vertices. And if it's a directed network, then the connections have directions. All right, so for example, let's do a simple directed network with 3 vertices, which we'll call K, L, and M. And let's say they're connected, and they're going to be connected with directions. So let's say K is connected to L, so we indicate the direction with an arrow. K is also connected to M, and K is actually connected to M twice. L is connected to M, and L is actually connected to itself, and M is connected to L. All right, so there are our connections with the directions, with the arrows indicating the directions. All right, what we're going to do is represent the directed network with a matrix. And in order to do that, we call this the adjacency matrix, because it's going to show us which vertices are adjacent to which vertices, which ones connect. So we're just going to set up our matrix. So we're going to go from K, L, and M, and then to K, L, and M. So we're going to have a 3 by 3 matrix, and we're just going to put in here the number of connections from this vertex to this vertex. Now from K to K, there's no path, one stage path. There's no direct connection from K to K. So we have a 0 here. From K to L, there's just this 1. And from K to M, there's these 2. So we'll have a 2 there. All right, so the adjacency matrix is each entry represents the number of direct paths, or what are referred to as one stage paths between 2 vertices. All right, so from L to K, we have 0. And from L to L, there's 1, because there's this loop that comes back to L. And from L to M, it looks like there's 1. And then from M, there's only 1 out, which is to L. So to check to make sure we did it correct, the number here should equal the number of connections here. So we have 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we probably have them all. Now, what's kind of cool about this is that once we have the adjacency matrix, which we could call, let's say we'll call this matrix A, and remember A is showing the number of one-stage paths, we can multiply A by times itself, or do what's called A squared, And that will give us a new matrix that will show the entries, whose entries will show the number of two-stage paths. So what is this two-stage path? A two-stage path is how many paths there are, for example, from K to L, where we would go through, where we would take like 2 steps. So for example, I can get to from K to L by going K, M, L, right? K, M, L. I could get to L to K. Doesn't look like I can do that. Or I can get from M to K. It looks like I can't do that in 2 steps, right? But I could get to M to L in 2 steps. I could go to M, L. Or I could go, M to L to itself. So if I square this, I should get the matrix that will tell me how many 2-stage paths there are. And then if I cube it, how many 3-stage paths, and etc. That's what's kind of cool about this. Now, what are some of the applications for this? Like I said, one of the applications that we're going to see in the book is about airline routes or bus routes where we know the nonstop flights, and then we can use the adjacent matrices to figure out where we have 1 stop or 2 stops and how many different ways we can do that. So that's kind of cool. The other cool application is a food web, and I'm hoping that you know what a food web is. A food web is shows in an environment what foods animals eat. So sometimes they eat plants, sometimes they eat each other. So for example, here is a food web that is showing the relationship between fish and sea lions, killer whales, sea otters, and shellfish. So if you're pointing to something, then I guess it's a predator-prey thing. So sea lions are prey of killer whales. So if you're pointing to something, then you're a prey of that. So sea lions are prey of killer whales. Fish are prey of themselves. Fish are also prey of sea lions and killer whales. Shellfish are prey of themselves. Shellfish are prey of fish, and shellfish are prey of sea otters. Sea otters are prey of killer whales. Now, if we set up the adjacency matrix for this, it would look like this. So the S is for shellfish, fish, sea otters, sea lions, killer whales. And we can see that the from and the to represents that you're a prey of that. So we can see right off that shellfish are prey. And what's nice about the adjacency matrix that we can't really see necessarily in the directed network is how many things eat shellfish. So shellfish eat shellfish, fish, and sea otters. Sea lions eat fish, and that's all. Killer whales eat a lot of things, but nothing eats a killer whale. So once you have the adjacency matrix, you can kind of see who's at the top and who's at the bottom of the food chain. Killer whales don't get eaten by anybody. They're at the top. And then what we could do with this adjacency matrix is we know there's direct relationships to different things. So we know that, if something happened to shellfish, for example, that would, knock out this row. And then it could be that, sea otters are in trouble because they don't eat anything else, right? That's the only thing they eat is shellfish. So if something happened to the shellfish, we know the sea otters would be in trouble. And if the sea otters are in trouble, then something that eats sea otters is in trouble. So then what we might want to do is take this and find the square of that matrix to see the 2-stage paths. So we could see not just direct relationships, but 2 stages down the road. So if something happens to shellfish, directly it's going to affect sea otters, but that might have a direct effect on killer whales. And that's what's cool about using adjacency matrices. Oh, pretty cool. Math is pretty cool. I wish I taught math.